Okay. So let's get back to cardinality, if that's okay. And our idea for cardinality is that we say like two sets have the same size if there's a one-to-one and onto function between them. So that is what we have this notion of cardinality. So if you can find a one-to-one and onto function from A to B, you use the symbol like cardinality of A equals cardinality of B. Okay. Then we did things like we showed like we showed the basic properties. If the cardinality of A equals the cardinality of B, then we have like a symmetric property. The cardinality of A equals cardinality of A. We have okay, all that stuff. But then we can also say what it means to have cardinality less than or equal to. And that's if there's a one-to-one function from A to B. For some F. Okay. And we showed the same well, no, we didn't show this one. We show cardinality of A less than or equal to cardinality of A. Like this, we have and we also showed that anti-symmetric and this was a major theorem called the Cantor, Schroeder, Bernstein theorem. Okay. And there is kind of something missing, which we'll talk about later. So if I think of this symbol as being like regular less than or equal to, does anyone see a property that I have kind of skipped for less than or equal to? If I want it to be like true, if I want it to be like really less than or equal to, what is the thing that I'm missing? That is my question. I guess here's what we're missing. We're missing like either cardinality of A less than or equal to cardinality of B, or cardinality of B less than or equal to cardinality of A. For all sets A and B, actually, The reason why this is not one of the basic things we wrote down is because this requires, to prove this, requires the axiom of choice. Okay. Oh, just a minute. Oh, okay, never mind. Okay, so to give you an idea of like how you might try and prove something like this, I just want to give you a rough idea of what you would try and do. You might try to enumerate A as like A0, A1, and so on. Okay. And find B and B and set f of A0 equals B. Then find B1, which is in B minus B0, and set f of A1 to be B1, and find B2 and B minus B0, B1, and like f of A2 equals B2, and just keep on doing that. Find something in B that hasn't been mapped, chosen as the value of a function, like a value of f, and then choose that to be like the next value of f. Just keep on doing that. Okay, and this kind of proof sketch, there's a lot of problems with it. There's like two main problems. Well, they're kind of like the same problem, but I'll just tell you that not all sets can be like enumerated like this. The other problem involves like, how do I guarantee I can always choose this next B, given that I've chosen the first of the, like, how do I prove that I can make this function f? Okay, and then hopefully at some point, like either you've exhausted all of A or you've exhausted all of B. If you've exhausted all of B first, then you've constructed a function from B to A by looking at the inverse. If you exhaust A first, you have a one-to-one function from A to B. Okay. And if you completely match up everything in A and B, well, then they have the same size. You know, so you just kind of go like that. Okay, but like I said, this proof is not a real proof. There's problems with it, which we'll see later. Okay, so that's just to give you an idea of cardinality. And we saw like cardinality of finite sets. Okay. And what we showed was that like the cardinality of finite, like sets with finite cardinality, like they kind of match up with kind of the arithmetic of natural numbers, right? So let me remind you, we've shown one of the things we showed, well, it was a little bit difficult, but we showed that if S equals M and cardinality of S also equals N, then M equals N. And we also showed that N is not finite or it's infinite. meaning there's no one-to-one and onto function from a natural number to the set of all natural numbers. Okay. There's other things you can prove. Like, I'll just summarize some of the other things we can prove without proving it, because I want to get on to cardinal arithmetic and countability. So let me just, just kind of state some facts, right? So if X is finite and Y is a subset of X, then Y is finite. And furthermore, its cardinality is less than or equal to the cardinality of X. Okay. And here we mean like the cardinality of Y is a natural number, the cardinality of X is a natural number, and they're less than or equal to as natural numbers. Of course, since Y is a subset of X, its cardinality is naturally less than or equal to the cardinality of X. But here, this is like a statement about natural number arithmetic. Okay. Okay. And the idea of the proof is basically just to carry out the sketch, except the sketch kind of is fine because everything is finite. Okay. Anyways, the idea is you write X as like X0, X1, all the way up to Xn. Okay. Now choose Y0 and Y, or choose Xi in X to be such that Xi is in Y and I is the least possible I. Okay. And then you put Y0 equals Xi. And then choose your next Xi. Choose Xi. I guess I should put like Xj such that J is the least, where J is greater than I and Xj is in Y. And just keep on doing that. Like find the first occurrence of an element of Y and find the next one, call that Y1. Put Y1 equals Xj. And then find the next occurrence of Y, the next element of Y, call that Y2, and just keep on going. And eventually you've got to reach the end. Right? Just keep on going until Y is equal to Y0, Y1 up to Ym, with m less than or equal to n. Okay, this idea can be turned into a real proof if you carefully use the recursion theorem, but we're not going to do that. I'm just gonna say that it could be done. Okay. Okay, some more statements about arithmetic. Finite sets. F is a function. X is finite. And f of x is finite. And its cardinality is less than or equal to the cardinality of x. I guess this is a lemma. I don't know why, I don't remember why I call this a lemma, but oh well. X, Y are finite if X intersect Y is the empty set. Oh no, then we have, so in general, the cardinality of X union Y is less than or equal to the cardinality of X plus the cardinality of Y. Again, this is addition of natural numbers. This inequality is inequality of natural numbers. So X union Y is finite. And its cardinality is less than or equal to cardinality of X plus cardinality of Y with equality if and only if X and Y are disjoint. You know, other things for arithmetic like cardinality. If S is a finite set whose elements are finite, so the finite union of finite sets is finite. Which is kind of just a generalization of this lemma. This lemma says that the union of two finite sets is finite, and this theorem says the union of a finite number of finite sets is also finite. And we also have that the power set of a finite set is finite. I mean, in fact, you could show like that the cardinality of the power set is just 2 to the cardinality of X. But that okay, and then the last theorem I'll write down about finite sets is if X is infinite, the cardinality of X is strictly greater than N. Meaning there's a one-to-one function from N to X for all natural numbers N. Okay. And that kind of naturally brings us to the issue of countability. So this theorem tells us that there's a break between the finite sets and the natural numbers, which is an infinite set. Okay. Okay. So we have this kind of break between countable sets, between the natural numbers and the finite sets. We give anything with the cardinality of the natural numbers, we call that countable. So if the cardinality of X is the same as the cardinality of the natural numbers, we say that X is countable. And for finite or countable, we say X is at most countable. Okay. Okay. And you know, the first thing we want to do when we talk about countability. So let me give you a quick plan. Here's our plan. We want to see like the integers, the rational numbers, it's some other things are countable. We want to see that the real numbers are not countable. And then we want to talk about cardinal arithmetic. Okay. Which means we want to take the sizes of sets and we want to learn how to add up their sizes, multiply their sizes, and so on. And we like, as much as we can, we want to see what's the similarity between cardinal arithmetic and just like regular arithmetic of natural numbers. Okay, let's at least see that the integers and the rationals are countable. Let's start with the integers. So I guess this is like a theorem. The cardinality of Z equals the cardinality of the natural numbers. Proof. So it's clear that the natural numbers are a subset of the integers. So automatically we have this inequality. Now I want to define a one-to-one function from the integers to the natural numbers. So how do we do that? Define f from the integers, the natural numbers. Just define it to be f of x is going to be, let's say like 2 to the x if x is greater than or equal to 0. It's going to be like 3 to the minus x if x is less than 0. And this gives you a one-to-one function from the integers to the natural numbers. It's clear that like, so f, this gives you a natural number whenever x is negative, and it goes like, you know, f of minus 1 is 3, f of minus 2 is 9, and so on. And f of 0 is 1, f of 1 is 2, f of 2 is 4, and so on like that. So this gives you a one-to-one function from the integers to the natural numbers. And that proves that the integers have cardinality less than or equal to the cardinality of the natural numbers. Now the Cantor, Schroeder, Bernstein theorem tells us, Cantor, Schroeder, Bernstein theorem tells us that these two sets have the same cardinality. By Cantor, Schroeder, Bernstein theorem. Okay. Of course, there's a way to get an explicit like one-to-one and onto function between them. I just, you know, I can just enumerate the integers by going 0, 1, -1, 2, -2, 3, -3, 4, -4 like that. So, and I match it up with natural numbers like 0, 1, 2, 3, 4, 5, 6, 7, and so on, right? And you can like work out an explicit formula that gives you a one-to-one and onto function from the integers to the natural numbers, right? And that's fine too. Okay. Okay. Now let's prove that this equality later, because what we're going to see is that it just follows from like basic properties of cardinal arithmetic. Okay, but briefly, the plan is to write out like, let's see, how do you do this? To write out all the rational numbers you can. Well, this doesn't give you all rational numbers, but it gives you all positive rational numbers, but with some repeats, you know? So don't worry about the negative rational numbers, but if you just worry about positive rational numbers, you just count them off like by doing this. And then eventually, so the first one is 1, then 2, then a half, and you match up each of these rational numbers with a natural number. And eventually you'll hit all of the positive rational numbers. So this proves that the cardinality of the positive rationals equals the cardinality of the natural numbers. Okay. But we'll do it explicitly later. Okay. Now let's prove that the cardinality of the natural numbers, well, it's definitely a subset of the real numbers, but it's a strict inequality. Okay. And in fact, let x just be the interval 0 to 1. So we'll show that the cardinality of the natural numbers is strictly less than the cardinality of x. And the cardinality of x is, well, x is a subset of r, so the cardinality of r is greater or equal to that. Okay. And this is like a famous theorem. It's called Cantor's diagonal argument. So let's like write it down. We have this theorem. A proof. So F, I'll assume that we can write the set of all the real numbers between 0 and 1, assume that we have a one-to-one and onto function from the natural numbers to the set. So enumerate them as x0, x1, x2, xn, like that. Okay, now write each of these xi's in decimal as a decimal expansion. So it's going to be like 0 point AI1, AI2, AI3, like that for I equals 0, 1, 2, etc. Okay, and also we have to make like some convention, like we have to make sure that we write all our decimals like so that they don't end in all 9s. We're just going to assume that. Okay. If something is eventually going to be all 9s, we're going to change it around so that it ends in all 0s. Okay, but yeah. Okay, so now let's like write down all our decimals. We have x0 is just 0.A01, A02, A03, so on. And x1 is A11, A12, A13, so on. And x2 is like 0.A21, A22, and so on. And then xn is 0.AN1, AN2, and so on. These are the decimal expansions of the xi's. Okay. Now I want to construct a new decimal. So let's put y0 to be either it's going to be 3 if A01 is equal to 2. It's going to be 2 if A01. Oh, sorry. No, it's going to be 3. Oh, sorry. I guess it should be 2 if A01 is not equal to 2. It's going to be 3 if A01 equals 2. Yes, that makes more sense. Okay. So y0 has a different first digit than x0. That's what this says. Well, we're going to put y1. It's going to be 2 if A11 is not equal to 2, and it's going to be 3 if A11 equals 2. I'm going to keep on doing that. So yj is going to be 2 if, oh, sorry, I didn't want to put A11, I wanted to put A12. Yes. In general, if aj, j plus 1 is not equal to 2, we're going to put yj to be 2, and it's going to be 3 if aj, j plus 1 equals 2. I'm just going to keep on going, and then let y just to be 0 point y0, y1, y2, and on like that. Okay. And notice that in the decimal, if we compare the decimal expansions of y and any of the x's, they differ at the place that we've specified. Like y is not equal to x0 because their first decimal places are different. Y is not equal to x1 because their second decimal places are different. And because we've chosen the decimal place to be 2 and 3 only, like there's no way for like, you know, the decimal place, this decimal place is 0, and while this decimal place is 0 while the other one is 9, but they're equal because of like some 0.99999 equals 1 thing. You know, we've kind of eliminated that by only choosing 2s or 3s. Okay, so y is not equal to, or y is not in, it's not x0, it's not x1, it's not x2, it's not any of them. But y is a number between, is a real number between 0 and 1. So this is a contradiction. This is a contradiction. So there's no way to get a one-to-one and onto function from the natural numbers to this set. So there is a one-to-one and onto f from the natural numbers to this interval, like that. Okay, and that is called Cantor's diagonal argument, because, you know, we choose our decimals so that it like it doesn't match. Like you go down the diagonal of all the decimal places and kind of adjust it slightly. Okay. So let us now take like 5 minutes, a 5-minute break, and then we'll talk a little bit more about cardinality after. Okay, so I will be back, let's say at 4:27. Okay.